that's the whole thing. Because, well, it was from two drafts. One which takes track of data, one which is very scrap. And YouTube, I took it. No. I said, look, I got an experiment. What I have to write 2 boxes. You see, one doc that clears the deck of the experiments, and then the 2 other boxes. Flip side is, so here's that was your experiment should not be standard track. Which means that this but you're starting with you're starting with case scoring. It didn't use extract. You don't have to worry about Iccrg.
All right, folks, let's get started. Can somebody get the doors in the back? So this is welcome to the ICCRG session in IETF 102. If ICCRG is not the meeting you want to be for, then you may still want to be in the room. It's fun, I promise you. Very quickly, the blue sheets are out. Please put your name down. Note well. I'm assuming everybody knows what the note well is. I'm not going to read through this. But if you haven't, you should definitely read this before you participate, before you open your mouth here. We have several presentations today, and it's kind of it's a full agenda. So I'm going to try and hold everybody to their times, allotted times. Please bear that in mind as you're presenting. I'm going to be very tight on the presentation times. Before we get going, though, I need 2 volunteers as usual. JavaScribe. I need a volunteer. Thank you, Miria. Minutes. Thank you, Stuart. Excellent. We can move forward. So we have many exciting things on the agenda today. I believe all the speakers are in the room. Not all of them, but we have. We're going to start off with. Not slow start. Bob and Joachim are going to present pace chirping as a new way of doing startup. Roland Bless is going to talk about policy-oriented AQM steering. Neil and Ian are going to talk about BBR, first an update, and then BBR startup behavior. And then Ilpo is going to give us a brief overview of FASOR and congestion control that may have relevance. This is actually, it's not yet a working group draft, but it's something that's happening in core that Ilpo wanted to share with the ICCRG community because it basically is about congestion control, or at least has intersections with it. And then if we have time, Brian will have the floor to talk about how to make things better and how to kill some other things. With that, let's get started. Any questions before I actually get started? Any questions on the agenda? Wonderful. Okay, take it away, Bob. Let me get this one. Yep. Bob, use this and get closer to the mic. Yeah, grab this. It's not working? Where's the switch?
Right. Okay. All right. Go, man. Yep.
Hi. My name is Joachim Isse. I completed my master's degree at the University of Oslo in June, and my thesis was about pace chirping. Is it possible to adjust this mic? Because it's really
Tell you
low.
what, why don't we, as I'm going to start.
Yeah, okay. And then we'll
Because right, okay, right. Just sort of, I think everyone in this room knows that there's this dilemma. The more you try and accelerate the flow at the start, the greater the overshoot you get. You get one round trip time before you discover that you got it. Yeah, that's sort of the received wisdom of slow start in TCP, and not just TCP. It's a general dilemma for any flow trying to start in the internet without explicit signaling, which is a feature of the internet, not a bug. The lack of explicit signaling, that is, not the overshoot. So you can sense you're getting delay and stop earlier, and that's what something like hybrid slow start does, but then you get slower convergence. And so what we're having to present today is pace chirping, which escapes this dilemma. And I did that photo montage many years ago, and it's actually extremely applicable to this talk, where you're trying to accelerate up across the length of a swimming pool. You're screwing up everyone else, and you're also going to hit the end.
Why do you have a belt in your swimming pool?
I didn't hear the question. Oh, okay. Right. Okay, so we're going to start with some results that Joachim did, just to give you an incentive to listen to the rest of the talk. These are flow completion time results on the left and Q delay results, CDFs of Q delay on the right, cumulative distribution functions. Let me try and quickly explain all the axes. On the, let's do the left plots first. You've got flow completion time on the left, and sorry, on the vertical axis, and file size on a log scale in kilobytes on the bottom, and the three levels of plot, the intensity, which, see if I can find the red button, there we go. The intensity, that 1000 there means 1000 milliseconds average between each flow start. So it's getting more intense as you go down. This is 100 milliseconds between each flow start. It's a Pareto distributed file size and exponentially distributed time between the flows. I think it was alpha 0.9 for the Pareto distribution, wasn't it? Yeah. 0.5. Okay. Right. Oh yeah, because that's right. Yeah, we found a paper that characterized current internet since HTTP2 flow sizes. So we tried to match the distribution to that. Right. So the oranges, if you can't read this, is with pace chirping, and the greenish thing is data center TCP, which has a very good low queuing delay. This is the CDF of the queuing delay in the same experiments. And the final thing I need to explain is the difference between the two columns in each experiment. One's with no background flow and one's with one background flow, just an infinite running flow, right? And so probably more realistically, you're dealing with the 0, but sometimes you've got a long download, you'll be dealing with the 1. So you can see pace chirping gives you significantly faster flow completion time. The green line, by the way, is the sort of ideal, the maximum or the minimum flow completion time you would be able to get at that bit rate. So we're getting pretty close to it, whereas data center TCP is pretty far off. So next, no, I've covered everything there. So before we get into how it works, I just wanted to talk a bit about applicability, because because I'm at the mic, people probably assume this is about ECN, right? And it isn't, right? We're just using delay-based, and that was because for a flow start, you don't actually know what the capability of the bottleneck is. You don't know whether it's got ECN until it's too late. And this is the same with any. There are a myriad of different attempts to solve this problem with some clever new signaling from the bottleneck. But the trouble is, on the internet, are you going to hit that bottleneck, or are you going to hit just a dumb bottleneck tail drop queue? So we wanted to just stick with something that was common to all queues. But of course, it's still not applicable to policers, right? But this is research. Having said that, because we're getting a very low additional queuing delay, we're adding about 2 or 3 milliseconds typically on a 20 millisecond path. There's a footnote there that says exactly what that means. But that means we're most interested in cases where our bottleneck is already getting us a low queuing delay. And so that's particularly interesting in something like a data center with data center TCP holding the queuing delay low to start with, because there's not much point making sure your additional queuing delay is low when your general queuing delay is high, right? And the other case is with the L4S dual queue coupled AQM with the similar data center TCP-like traffic over the public internet. So in other words, where you're isolated from TCP's general high queuing delay, and they're the environments we're more interested in, and that's why we've used data center TCP in these experiments and things. But we've open sourced the code because we realized that this is now, it does seem to be applicable to the general internet because it's only delay based. So if you wanted to try it in your own environment, you could. But you won't see that in this particular talk. All right. I guess the other point about applicability that needs to be made is that when you're getting the additional queuing delay very low, it does mean that you can have shallow buffered switches without getting lost. And I prefer to say it that way rather than if you've got shallow buffered switches, you won't get lost, because I would have thought you put in the size of the buffer you need rather than the other way around. But so I think the summary of this whole slide would be general applicability. Now we come to the caveats. As I said, this is research, that's why it's in ICCRG. But the reason we're coming to ICCRG is that I think it prompts, it's very tempting, it's got very good results, and so it prompts some discussion on what do we need to do to make this happen. It's certainly not production ready. We've only focused on proving the concept at this stage over the period of Joachim's master's thesis, which was a one-year project. And there are many issues. They're listed at the end, but the two main ones, just to save you coming to the mic and pointing them out to us, is delayed acts, because we're measuring differences in delay for each packet. Delayed acts mess us up. So we try and, for these experiments, we've just turned them off. But obviously on the internet, you'd have to coordinate with the other end somehow to do that. And the other one is bursty max and bursty schedulers, which we haven't dealt with. We've only dealt with simple Ethernet type links at this stage. We have tried it over Wi-Fi and over the general internet, and it seems to work, but we haven't done any formal experiments with these sort of Macs. All right, so at this stage, I'm going to pass over to Joachim, and he'll tell you how it works.
And first, I will adjust the mic. That's a pretty good height. So I introduced myself earlier, and now I will try to explain how pace chirping works. And it's really simple, but it might take some time to understand. So the basis for pace chirping is packet chirps. And here we see a plot of the interpacket rates of a chirp. So a chirp is basically a sequence of packets sent at an increasing rate. So in this example, we have a 16-packet chirp, and there's a geometry, which is a variable that controls the span of the rates in the chirp. And the goal with these packet chirps is to continually pulse the queue by a few packets and then relax, and then use the behavior and the information you get from the packets and the acts to measure the available capacity of the bottleneck. And with a chirp, you can actually measure both the available capacity and the maximum capacity. And the ultimate goal of this is to maximize the ratio of capacity and information to harm. And in this case, this is queuing delay. So you want to get as much information with as little queuing delay as possible. So if you have any questions, if I'm not being clear, please come up to the mic and ask me. So that was the basis. And this shows how the chirps interact with the bottleneck and how the sender and the receiver observe the packets in the chirp. So in this case, we have multiple chirps sent after one another. And from the sender side, you can see that the chirps has increasing rates. But once they traverse the bottleneck and arrive at the receiver, the rate is limited by the bottleneck. So you can use this to measure the available capacity at the bottleneck. This is not exactly how we do it in pace chirping. This just demonstrates how we can use chirps and how they interact with the bottleneck. So let's go to pace chirping, put all the chirps together. So the basic idea is that we have multiple chirps distributed over a round trip, and we maintain a average rate or an average gap using a EWMA. So that's basically a EWMA of each measurement from each chirp. And each chirp gives you some information, but that information is very noisy. So you have to have multiple chirps to actually get useful information. The first 3 rounds consist of 2 chirps or bursts. And then in the second round, you can set a marking packet, and you have another 2 chirps. And in the third round, you have another 2 chirps. And from the 4th round, the algorithm runs itself. And I'll come back to the number of chirps on the next slide. One thing to note here is that the queuing delay caused by the chirps is solely dependent on chirp geometry. And I also want to note here that the chirp length reduction in the plot is due to or it demonstrates what's happened when the estimated rate increases from one round to another. So the growth in the number of chirps per RTT depends on the gain variable. So every RTT, we increase the number of chirps with a gain variable, and this can be used to accelerate either faster or slower. So actually in the previous plots, when we went from the third to the fourth round, we had a gain of 2, which meant that we doubled the number of chirps. And this also shows that it's possible to have a gain of 2.5, which creates 5 chirps instead of 4. So the more stable the measurements are, the higher the gain, or you can have a high gain, the more confident you are in the measurements. Another thing about page chirping is that we try to push in a little harder than what we push in a little harder than the available capacity grows, and there are 2 reasons for this. The first one is to make other flows yield, and in the future, when we do more experiments, we would like to make activity trigger link scheduler expand the capacity. And again, the queuing delay solely depends on the chirp geometry, not the gain. We shift from page chirping to congestion avoidance and NAC clocking when the chirps fill the round. So, and this is something we will continue working on. It's not perfect yet, but this is what we currently do. So this demonstrates a small short flow using page chirping, where each vertical line is either a chirp or a burst. The 2 first vertical lines are 2 bursts. The y-axis shows the packet gap, and the top one is the inter-send gap at the server, and the bottom one is the inter-receive gap at the client. And you can see that the inter-packet gap at the client is bounded by the capacity. So all the packets that are sent faster than the bottleneck will get queued, and this can be detected using the returning axe from the client. So what do you get using this approach? You get fast convergence and low queuing delay. These plots shows the throughput and the queuing delay of 4 flows started after one another. And if you look at the first flow, it reaches the capacity with virtually no queuing delay. The only queuing delay is from the chirps. And as you can see, there's almost no queuing delay. The second, third, and fourth flow has to push the other flows back. So naturally, it creates more queuing delay, but it's not too bad with 5 milliseconds of queuing delay. Oh, right, sorry about that. So in the throughput plot, you have, it's a 115 megabit link, and the x-axis is actually in round trip times and not in time. So yeah, on the bottom plot, you have queue size in milliseconds. It goes from 0 to 6, and on the x-axis, you have round trip times, as with the other plots. That's not clear. Please ask questions.
Roland Bliss, KIT, sorry. Just clarification question. Are these results from a simulation or experiment? No. Or?
It's a real test bed. Okay. So we have a physical test bed with 5 machines.
Neil Cardwell, Google clarification question. What's the
pacing is a module that uses that, right? And I guess making that into timing wheels and all the rest of it would be well possible. There's advice in the thesis on how to disable kernel pacing rate calculation, how to disable responding to C marks and things like that, which was actually quite a difficult part of it, because there are assumptions built into the kernel that of how slow start works, because it's been around for so long. And that's it.
Thank you so much, Bob. Yeah, thank you. I'm sorry.
There on your first presentation ever, you know.
Well, lovely. Let's give it up for Joaquin. So if the remote participants can hear me, can somebody, well, if the remote participants can hear me, I don't know how to bring it back. It was, but then it went away, and I have no idea how to bring it back. Right, so hopefully they can hear me. That's wonderful to know. They probably know by now, but we had a power outage here, and we are back. Can they see the slides? Does anybody know if they can see the slides? Well, not yet for the next. But anyways, hopefully you can see the slides. If not, hopefully we'll be able to, they can see the slides. Wonderful. So they can't see our faces, which is probably a good thing anyways. Lovely. Okay, moving on. Roland, sorry, before you start, Roland, we might extend the session about 10 minutes into the break. I hope you understand. And if that happens, I'll still try to keep this tight, but let's move on.
Yeah, hi. My name is Roland Bless from KIT. I'm presenting policy-oriented AQM steering, which is joint work with Mario and Martina. This was presented this year's networking in Zurich. So the motivation is basically starting with AQM. So we have newer AQMs like CODL, Pi, and also GSP, and they try to be parameterless. And they work reasonably well over a wide range of track situations. Though they have one crucial parameter remaining, which we will call for now the target delay set point. So CODL, for example, has typically a default value of 5 milliseconds of the target delay. And the achievable performance basically depends on the current traffic situation. So it varies with the number of flows and also their RTTs. And so potential outcome is, depending on the traffic situation, either you have unnecessarily large delay with a fixed set point or underutilization. And so AQM steering tries to actually improve that AQM performance by providing an external control loop around the existing AQM. So on the right-hand side, we have that normal AQM with its control loop. And then it interacts with the TCP congestion control loop. And AQM steering is rather meant to be an external control outside the AQM. So what it does is basically it gets current values like the observed delay or throughput or events like packet drops, for example, and then it calculates a new target set point given specific policy, which basically comprises utilization, desired utilization, and a maximum delay. I'll come to that later. So the idea is basically to adjust that target delay set point of the AQM instead of doing some optimization inside the AQM. So it's basically applicable to these different AQMs that I mentioned in the beginning. So what is a target delay set point? So just to get a rough idea that newer AQMs try to keep the queuing delay around the specific target. And so we have this visualization of the bottleneck buffer, or at the bottleneck buffer. The amount of in-flight data is on the y-axis. And usually if there's excess data, so you're sending more data than your bottleneck will be able to process, the packets will be put into the buffer. And so the AQM then observes queue length or sojourn time, have you. And this is basically here the target delay set point. So if that is exceeded, the AQM will start dropping packets or marking using ECN, for example. So an example for this AQM could be the global synchronization protection, which was submitted as draft, and there's a paper, but it's not has been standardized so far. It simply drops packets if the target delay set point is exceeded, and so then tries to dynamically find a suitable dropping rate. So the basic idea of AQM steering is now to just adjust this target set point. So in this case here, we have a situation where we have underutilization. So if you have only a few flows, AQMs usually lead to underutilization because either we have too much synchronization, so to say, or even you have only one flow, so the back office may be too high. So the current used congestion controls may lead to underutilization in this case. And so what AQM steering now can do is basically find a better set point by increasing that set point to a higher value, and then we basically get full throughput again and avoid that underutilization. On the other hand, if we have lots of flows and we have good loss desynchronization, then maybe the set point is even too high. So we can basically lower this set point and then achieve the same throughput at a lower delay. So coming back to the policies, basically we have that trade-off throughput versus delay with a given fixed set point, and then you can choose either one. So the idea of policy-oriented AQM steering is that we have then easy-to-grasp policies, like you can define a lower utilization target and a maximum queuing delay that you're willing to accept. Optionally, we have also defined upper utilization targets. So if you want to have ultra-low delay, meaning you're basically below 100% utilization, you can also specify that. And so you have meaningful parameters, like how much delay am I willing to trade for high throughput, or at which throughput I'm not willing to trade delay anymore. So AQM steering tries to find the best throughput delay trade-off within these given policy bounds. So the challenges that we were facing is basically when should the set point be assessed or adjusted, and which value should the set point be changed. The third point, I have no time, unfortunately, to talk about this, how to achieve these ultra-low latencies. Basically, we're using some kind of virtual queue for that. So challenge one, when to assess or adjust the set point. So AQM steering observes basically the interplay between AQM and the congestion control, and on the left-hand side, basically we have in this situation no bottleneck, so when there's nothing to do, no packet drops. And on the right-hand side, we're in a situation where the current queuing delay is way above the target, and the AQM needs to do its work, and so we have to wait until AQM steering will do anything. So it has not converged yet, and so we are waiting until it's more or less converged. So if it's the actual delay is fluctuating around the target, then we think more or less we are in a situation where AQM steering then can do its adjustment if necessary. So how do we determine the new set point? That we need basically different strategies for increase and decrease. So decrease is much easier because we can basically calculate the amount that we can lower the target set point. We need some smoothing, averaging, and so on, but that's basically fairly easy to do. The increase is so raising the set point is much harder because it basically depends on the BDP or RTT, which is not known by the AQM. So we just use an iteratively mechanism or iterative mechanism in order to try to find the right set point here. So we need some kind of probing. We implemented that and evaluated that in a small test bed here. So we used that GSP AQM because it's fairly easy to understand how it works. And put the AQM steering as control loop around that. The implementation used the DPDK-based switch, which is here, also the bottleneck. We have a sender and a receiver. We have several times 10 gigabit per second bottleneck link, and a 50 millisecond round trip time. We compared basically the GSP-AS with a lower utilization, with a utilization target of lower utilization target of 99% and a maximum allowed delay of 30 milliseconds. Then we compared this to CODL and GSP with a fixed set point of 2.5 milliseconds, and also with a small tail drop buffer the same size and a large tail drop buffer of 30 milliseconds. So I present just briefly two experiments. One is just showing for steady state long-lived flows. It's working as expected. So GSP is able to find the right setting according to the policy, while the regular AQMs, their performance depends on the traffic situation. And for tail drop, it basically depends on buffer size. But then you have either high throughput or low delay, but not both at the same time. And experiment 2 is about the transition behavior. So here in experiment 1, we have on the left-hand side the throughput, and on the right-hand side the queuing delay. And we varied the number of flows present at the bottleneck. And the leftmost bar here is the small tail drop buffer. The rightmost bar is the large tail drop buffer, and then we have CODL and GSP, and the dark green bar here is GSP-AS. And as you can see, with basically 2 flows, GSP-AS achieves higher utilization than the static AQMs, and needs to invest there a little bit of queuing delay here, lower than 10 milliseconds. So we have a low number of flows, and so we can only have low loss desynchronization. With 9 flows here, the situation is better. So the normal static AQMs perform also quite well. And GSP-AS adjusts also to a low value here. So that works as expected. While the tail drop buffer still suffers from underutilization. And for 36 flows, we have a high amount of loss desynchronization that is achieved. And in that case, GSP-AS or AQM steering can even lower the delay. So I will zoom into that so that can be seen a bit better. So the other static AQMs have still their queuing delay around 2.5 milliseconds, while GSP-AS then lowers the queuing delay to 1 millisecond here in this case. And just to give a brief overview of the transition behavior, so we have a situation here where we change the number of flows from 2 to 36 and then back to 2. And so we're starting with 2 flows. Set point is around 11 milliseconds for the target set point. And then as the number of flows increases, we smoothly adjust and lower the target set point, because we can achieve basically the same throughput with lower queuing delay. And then we have a situation where there's not much adjustment here. And so it's quite okay to keep that. Then once the 34 flows disappear, Cubic here basically needs some time in order to reclaim the free bandwidth. And so the AQM steering kicks in as soon as the AQM becomes active. And in this case, we see a stepwise increment here in order to find the right queuing delay, which is then, or a target set point, sorry, which is then around 10 milliseconds in order to achieve the lower utilization goal. Right, so yeah, this basically also concludes my talk. So AQM steering tries to improve existing AQMs and tries to find the best trade-off, throughput versus delay under a given policy. It's basically operating as external control loop around an existing AQM. And we did some evaluation in physical high-speed testbed using several 10 gigabit per second. And yeah, there are much more details in the paper, so if you're interested, you're invited to read that, and I'm here for questions.
We have time for maybe a couple of questions, just a couple of minutes.
Neil Cardwell, Google. Do you have any evaluations with FQ coddle instead of single Q coddle?
No.
Okay. I would, if you have time at any point, I would recommend using FQ coddle. The coddle authors recommend against using single Q coddle and recommend FQ coddle as the preferred solution because of the the way it isolates different flows into different queues.
Yeah.
So it'd be interesting to know how it looks in that case. Thank you.
Yeah, we just want to show for pure AQMs how it works, and yeah, thanks.
Yeah, Bob Briscoe, I'm wondering whether there's something we can do inside the control of the AQM to limit the amount that the outer loop has to do. For instance, this idea of having to have a fixed delay target, you can work out, you don't need to know the number of flows, if you like. The higher that the congestion level is, you can make that delay target higher, or more conversely, the lower the congestion level is, you can make that delay target lower. In other words, it can be a function of P rather than being constant. And that deals with your number of flows. It doesn't deal with your round trip time variation, but at least part of the AQM can be made.
Yeah, we actually, so our implementation was basically integrated into the AQM, so you can do that. But the general idea was to have a control loop which is on a much larger period of time instead of, I mean, otherwise you may get oscillations, right? In order, so we want to wait until the AQM actually did its job, right? And so then we are observing on larger time scales what we can do.
What I'm trying to argue is that a fixed delay target may be the wrong thing anyway for AQM to do its job.
Okay.
Given the whole point of what you're trying to do is adapt something that, I'm just saying, part of it maybe we can improve in the internal algorithm before but the round trip time dependence we probably can't, but because we don't know the round trip time, but things like the number of flows is represented by the congestion level, so that should be possible to do immediately.
Yeah.
Thank you, Roland. Neil, you're up next.
Hi, my name is Neil Cardwell, and I'm going to give a quick update on recent research involving BBR at Google. This is joint work with my colleagues at Google, Yu Chang and Stephen and Sohail. The quick BBR folks, Ian and Jana and Victor. I guess Jana is now an alumni at Fastly, actually. And PR and Yusuf.
Not alumni at Fastly.
Oh, well, alumni of the Google BBR team who's moved on to greener pastures. This is work also done with PR and Yusuf and Kevin and the TCP team, and then our senior researchers, Matt Mathis and Ben Jacobson. So I'm just going to start with a quick overview and status of BBR at Google, and then try to spend the majority of my time on an update talking about research goals and focus areas for our group, talking about some design rationales for the current prototype V2 code, and show some lab results to sort of illustrate the behavior of the current pre-release code that we're experimenting with. So as far as BBR version 1, it's something we've talked about at the IETF in the last couple of sessions. It's used for TCP and Quick on google.com and YouTube. It's also used for internal traffic between Google's WANs internally. It's available for Linux TCP and Quick as open source. There's also active work at Netflix going on for a TCP BBR implementation for FreeBSD. And then we've written some drafts documenting the version 1 algorithm and talked about it at previous IETFs. And there's a little paper in the CACM with an overview. So our current research is focused on a couple things. First and foremost is improving coexistence and fairness with loss-based congestion control, such as Reno and Cubic. And the main technique we're looking at is adapting BBR's bandwidth probing timescale for better coexistence. We're also looking at just generally reducing queue pressure, meaning packet loss and queuing delay. And there we're primarily looking at incorporating loss and ECN signals for 2 different mechanisms. One is a new model for estimating a safe range for in-flight data, and one is an estimator for exiting startup faster. And then we're also looking at speeding up the convergence of the min-RTT estimate by making our probes more frequent, and reducing throughput variance by making our RTT probes less drastic. So if I had to summarize the design principles that we're trying to adhere to for the V2 design, here's a quick list. I would say first we want to try to leave some headroom for other traffic so that there are queue slots or pipe slots for entering flows to grab, whether those are intermittent traffic, short flows, long flows. We'd like to let them come into the path and get some capacity without hopefully causing too much queuing delay or loss. We'd also like to react quickly when there is an apparent congestion signal, such as loss or ACN, to adapt to the delivery process that we're seeing right now to try to maintain flow balance in cases where we might be congested. And I should say that I've highlighted here in bold the principles that are new in V2, and the others are sort of carryovers from the V2 design. As in V1, we want to make sure we try not to overreact to loss and ECN signals. We don't necessarily want to do a multiplicative decrease on every round trip time where we get just even one of those signals. A new principle we're putting into play here is to try to probe deferentially, you might say. We'd like to do our bandwidth probing on a time scale that will hopefully allow decent coexistence with Reno and Cubic. But we still want to continue to probe robustly, you might say, to make sure that we have a nice robust probe at or beyond our existing maximum bandwidth or volume estimate before we sort of fall back to and cut our estimate of those parameters. We also want to try to avoid overshooting. So when we're doing our bandwidth probing, we want to start at an in-flight level that's previously been measured to be tolerable in terms of loss or ECN signals. And finally, we want to make sure that we continue to grow scalably. So here, a new aspect is that we want to try to start our probing gently with just one extra packet. That as we can grow in flight, apparently without seeing congestion, we want to sort of accelerate and grow exponentially to use any newly free capacity as efficiently and quickly as we can. So you may have noticed that a sort of one thing that all of these new design principles have in common is that they essentially need an explicit and independent model for a safe range for in-flight data. And in BBR version 2, right now the model is sort of composed of 3 different parameters. First, we want to make sure that we try to mostly spend the life of a BBR flow cruising at an in-flight operating point that tries to maintain flow balance and also leave headroom for other flows. And to do that, we have a parameter that we call in-flight low, which is essentially a conservative in-flight bound that's based on any recent loss or ECN signals we may have received. And then, of course, like any congestion controller, you eventually need to probe to see if you can get more capacity. And so we want to periodically probe beyond the level of flow balance to probe to see if you can get a higher volume of in-flight data, a higher bandwidth, et cetera. And to do that, we have a parameter called in-flight high, which is essentially a max volume of in-flight data that the flow had recently in flight before it started seeing signals of congestion, such as loss or ECN. And then finally, while we're probing for bandwidth, we want to do that in a sensible way. So if while we're probing, we don't trigger apparent loss or ECN signals, we'd like to grow our probing rapidly. So the in-flight probe parameter sort of controls the incremental amount of extra data we put in the network as we're probing to start small and grow over time. So just a quick run through of the typical life of a BBR flow. And you'll notice that a lot of these states are similar or the same as BBR version 1 at a high level, but some of the details of the mechanisms have changed. And the new stuff I've highlighted in bold here. So as in V1, in V2, a flow starts in a mode that we call startup, which is very much like traditional slow start in the sense that the flow is going to be doubling its sending rate and in-flight each round trip. The new piece here is that we do try to set our in-flight high to an estimated max safe volume of in-flight data if we do see one of 2 signals, either the filtered loss rate, current loss rate is too high, or the ECN mark rate is too high based on configured parameters I'll talk about later. And we're going to exit that mode when either we set in-flight high using those mechanisms, or there's the existing mechanism from version 1 where if we see a plateau in the delivery rate from the bottleneck, we estimate that we've filled the pipe. So after that, just as in version 1, we enter a mode called drain, where we essentially pace at a lower sending rate to gradually drain any excess in-flight that's beyond our estimated BDP until we've hit our target in-flight that's our estimated BDP. And at that point, we enter the what we call the probe bandwidth mode, which has a couple different phases that sort of go in a cycle over and over. And in V2, in probe bandwidth, we're essentially trying to cruise at an in-flight operating point that's respecting a couple of different constraints. So number 1, we want to keep the in-flight right around the estimated BDP if we can, and that's sort of our default mode and our starting point. But number 2, as I said before, one of our goals is to leave some headroom for other traffic. So if we have seen some loss or ECN signal that gives us an estimate of an in-flight high estimate for a ceiling, then essentially we calculate, we want to leave 15% headroom, and we can talk about the parameter in the Q&A if people are curious. But so that we try to keep our in-flight 15% below in-flight high. And then third, we want to continuously adapt our in-flight as we see loss or ECN signals as we're cruising along, keeping our in-flight below in-flight low. And that's adapted downward on either loss, in which case we respect packet conservation to try to maintain flow balance by decrementing the in-flight low by the number of packets lost, essentially. Or if we see an ECN signal, then we cut in flight as well. And here the current thinking is to do something like the exponentially weighted moving average of ECN mark rate, which is similar to DC-TCP. The current thinking is that we will probably want some sort of hysteresis. So because we'd like BBR to work well over wide area networks, and we imagine that if a WAN flow has an RTT of 100 milliseconds, say, in a healthy network, there will probably be some local area flows sharing that bottleneck that might be causing the bottleneck to go through a cycle of some ECN marks, a while with no ECN marks, and it could go through several of those cycles over a single round trip time. And in that case, the WAN flow might see that every single round trip time has ECN marks, but I think in those cases we won't necessarily always want to slow down because there might be free capacity. So I think there probably needs to be some sort of hysteresis. We want this to work over wide areas, so that's why there's that hysteresis term there. So when the ECN mark rate is above that hysteresis, we want to cut our in-flight in some fashion that's proportional to the mark rate, similar to something like DC-TCP. Okay, so that's the sort of steady state or phase in which a flow spends most of its time. And then, of course, we need to probe for bandwidth periodically, and also correspondingly probe to see if we can put more packets in flight. So the idea here is that when we're doing that probing, we want to grow beyond in-flight high slowly at first, and then increasingly rapidly if we seem to have more capacity. So in this mode, we set an in-flight target at each point in time. That is our current in-flight high estimate plus this in-flight probe parameter that's going to govern the acceleration of the probing. And that in-flight probe is going to start small, one packet, and then increase exponentially over time until such point as we see one of the termination conditions. So one of them is that if we see a loss rate that's too high, above whatever configured tolerance for loss is settled upon ultimately. Right now we're using 1% packet loss rate. If we see a packet loss rate go above 1%, or the filtered ECN rate is too high, then we say, okay, this is our ceiling. We're going to set in-flight high to this, and then we're going to terminate our probing phase. And also, if the the mechanism that's carried over from V1 is if our in-flight gets to be far enough above our estimated BDP that we estimate that we're building queue, that also causes us to terminate the probing, just like in V1. Yeah.
Gary Fairs, quick clarification question. What means too high for ETN?
Right. So this is that would be a parameter that would be to be determined. But yeah, and it's but yeah. Let's see. Next slide. So, and then finally, once we've terminated our probing, we think we've got we typically have a bit more in-flight than we would like. So we spend some time in a phase that we call the down phase of the probe bandwidth mode, where we hold the pacing rate below the estimated bandwidth to drain that extra data out of the network. And you'll probably notice that's very similar to the drain mode I mentioned. And in fact, currently in V1, the only thing that's different about those is the particular gain that's used for calculating the pacing rate. So actually the current plan is to probably unify those and use the same gain in each case. And I think Ian's going to talk a bit more about that, actually. All right, so that's the lifetime, that's the sort of life cycle of BBR flow. And just to give you a sense of how it behaves, here's a quick little example. So this example has 6 BBR flows in an emulated path with 100 megabit bandwidth, 100 millisecond round trip time, and a buffer that's 5% of the BDP. And it's sort of illustrating that you get some reasonable fairness convergence and a reasonably low retransmit rate And you can sort of see in the stacked or cumulative rate graph there at the bottom that below the 100 megabit line, there is a little bit of headroom there to left there essentially for to keep loss and queuing low and to allow room for entering new flows. So the next piece of the puzzle that I think is interesting and worth talking about is the question of how to coexist with loss-based congestion control. And here, the way we're sort of thinking about it now is that we want to have a goal of ensuring that Reno and Cubic can continue to work well in contexts where they do work well today. And specifically, we want to make sure that they continue to work well in intra data center or LAN environments, regular Ethernet spanning the range of values in use today. And also, of course, the internet last mile. And here we want to make sure that we support the common workloads where it's used today, certainly up to and including, say, 25 megabit 4K video at common broadband RTTs, let's say 40 milliseconds, for example. And the challenge here, if we want to coexist with these algorithms, is that Reno and Cubic need pretty long periods without packet loss in order to utilize high BDPs and maintain those bandwidth levels. So the strategy that we're taking is basically sort of a two-part strategy. So the first part of the strategy is to say, my primary goal is to estimate the bandwidth that's available to my flow. And then once I've done that, then the second thing I want to make sure I'm doing is to adapt the frequency at which I'm probing within some reasonable bounds, because any sort of probing that I do may well cause packet loss, right? And we want to adapt the frequency at which we risk that packet loss so that we're allowing Reno and Cubic flows that might be on the path to reach a bandwidth that is equal to ours. So that's the basic high-level idea. And how that's implemented is a sort of dual timescale model, including a sort of Reno pseudo-emulation, which is essentially the approach, very similar to the approach taken by Cubic, which has to solve a similar problem of Reno coexistence, right? So the basic idea here is that there are two different timescales that we keep in mind. One is what you might call a BBR native timescale on which it would like to probe. And we're experimenting with a couple different approaches here. One is a sort of time range of 2 to 5 seconds, as calculated as an increasing log-like function of our bandwidth. Another approach we're taking is a more randomized approach on a similar time window, or perhaps a little tighter, say 2 to 3 seconds. And then the second timescale is a sort of Reno coexistence or Reno emulation timescale. And the nice thing about Reno is it's very simple in its behavior. So, it's got this sawtooth where you can sort of get a pretty decent estimate of the timescale that a Reno flow with your RTT would need to maintain your BDP. And that's essentially just your BDP times your RTT. And so that gives you a timescale that you need to wait before probing again. Because if you want other Renos that might be on your flow, on your path to be able to achieve your bandwidth, you just need to wait that long. You need to at least make sure you wait that long before probably or perhaps causing them packet loss. But we do place a bound on that, which is where that cap comes in there, because we can't wait forever for our Reno. I mean, if it's a 10 gigabit 100 millisecond BDP, then you're going to be waiting an hour before you get to probe again, and so that's why we place a bound on it. Which is go ahead, Randall. So ahead.
Which RTT is it? RTT prop is a smooth round trip time or the last round trip time? Or?
Right. So the approach. So I've experimented with a couple different ones. The one that seems to work best is literally just counting packet timed round trip times, because of course there can be wide variation in round trip times. And when you start out, for example, your you're often at the end of a probing moment when there's a big queue, but that can all go away because BBR is able to drain all of that. So what it literally does is actually just count the number of experienced round trip times since it last probed, which is essentially what Reno is going to be doing as well. So that I think that works reasonably well.
Neil, before
Yeah.
you go on, just very quickly, you have 5 minutes left.
5 minutes? Okay. All right. So we take the min of those two time frames, and that's our time frame for probing. And then to go along with this, we need to co-design the bandwidth estimator filters timescale. And to work with this, basically, you just need to make sure you always have a bandwidth sample that covers a bandwidth probing period to be robust. And the simplest way to do that is just to have the window be literally the last 2 cycles, which makes it very simple. It's just 2 32-bit integers then. All right, so what does that do? So this is an example. You can consult the details later on, but basically here's a Reno flow and a BBR flow in a sort of broadband scenario. They reach a nice convergence with BBR taking about 48% of the bandwidth. This is and having nice low retransmit rate. And this is definitely an improvement from BBR version 1, which would have taken 92% of the bandwidth. And here we take a hair under 50%. Here's another example, just to illustrate. Here are 2 cubics, 2 BBRs. They reach a reasonably fair convergence with cubics taking a hair more than the BBR with low retransmit rate, pretty stable. And again, this is a big improvement over V1. So another thing that we're working on is exiting startup faster. Because I described startup earlier, you're sort of doubling your rate. You can have a lot of packets in flight. So that means once you start to cause loss, then you can cause any loss-based congestion control to back off quite a bit. So you want to exit startup quickly, both for reducing loss and for fairness. So V1 had this plateau criteria. The V2 prototype has both the loss-based heuristic, looking at whether the loss rate is both greater than the configured ceiling. We're using 1% now. And also there are enough gaps in loss gaps in around that it looks like signal rather than noise. And the ECN heuristic is basically just looking at the ECN mark rate and whether it exceeds some configured threshold. So I'll share some illustrations of how this looks. So here's a single BBR flow going into 100 megabit bottleneck, and it's starting up smoothly, hits the bottleneck, sees a clear signal, exits after 1 round trip time. It spent that round trip time of losses in packet conservation to not create any further losses. By the end of the round trip time, it's pretty sure it's filled, so it exits startup. This is this is an example of a third flow entering in a series of flows entering. And again, you can sort of see it, once it sees what it looks like a strong signal, then it goes ahead and exits here at 30 megabits, which is pretty close to its fair share of a third of the bandwidth, by the way. So we've also got some improvements for ProbeRTT that we're working on, because of this convergence can be slow because it probes only rarely, only every 10 seconds. And then there's a risk of high tail latency because it cuts in flight quite low. And the approach we're taking is, well, to make the probing less drastic. Instead of cutting down to 4 packets, say cut to 75% of the estimated BDP. And then second, we want to make the probing more frequent, say every 2.5 seconds. So to give you a sense of how that behaves, you can see over on the left, we've got the V1 behavior where they have these big drops every 10 seconds. And V2, the current prototype, basically has much more moderate drops every 2.5 seconds for much more stable behavior. And when we're going against cubic, the behavior is an even more significant improvement. You can see with the old V1 behavior, you can get some weird oscillation as it's settling in, but with V2, it's much more stable. So in conclusion, BBR version 1 is deployed at Google, and we're actively at work on V2. focusing on responding to loss and ECN signals, and on coexistence with loss-based congestion control. And we're always happy to see patches or hear about test results, etc. And always happy to collaborate with folks. Thank you.
Thank you, Neil. I have a thought. Let's hold off on questions. Ian, you're next with the startup. Why don't we do that? And then if we have time, we'll do questions together.
That's great.
All right, I'm Ian Sweat from Google. I'm only going to talk about BBR Startup. All the things I'm going to talk about are applicable to the quick code, and the experiments that I'm going to talk about are all in the quick code if you want to look at how the code actually works. And it's all open source in Chromium, which has a link. That's the implementation link. And it's also really mostly complementary to what Neil's working on. Neil's working on a lot of awesome stuff with the rest of the BBR team. But I have a few other use cases that I'm also kind of working on that are a little bit separate. So I look at a lot of web flows in particular, so very short-lived flows, and a huge portion just never exit startup, right? You send 20 packets, why would you exit startup? Or even worse, you're just constantly app limited, so maybe it is a long-lived flow, but you're sending 20, 40, 50 packets at once, and it's never enough to get out of startup. Flows on police connections can experience pretty brutal losses. So if you hit a packet policer and you start seeing really nice bandwidth, and then suddenly the policer kicks in, the loss rates can easily exceed 50% for at least short periods of time. This is not great for continuous delivery, and it's generally ugly, for lack of a better word. And also there's another issue for web flows is we've seen a few cases where ACK aggregation is so severe that we actually exit startup prematurely because we're not provisioning enough CWIND, and the ACK aggregation is kind of on a timescale that's so long. It's not quite as common, but it does occasionally occur. On the Quartz is WebRTC over Quick, and on the Quartz side, they're extremely sensitive to bandwidth variation of any sort. And one of the comments that they gave to us is our encoder can handle a bandwidth fluctuation of up to a factor of 2. And anything more than that is very painful. So a lot of the things Neil's working on, like making probe RTT less severe, would be hugely helpful there. But another issue we'll talk about later is like drain and other things. So the first idea is just make it more sensitive to loss. As Neil said, it already reacts to loss. In this case, I kind of took a different approach from what Neil did. I looked early on at trying to exit startup early due to loss. Like, if you've seen loss and it's been at least an RTT and you haven't seen a bandwidth increase or other heuristics like that. And those just generally did not work. I haven't actually tried Neil's proposal, so I'm curious to implement that as well. But the thing that I have that has worked quite well, both in traces and based on the kind of application metrics I have, is reducing the pacing rate. So the idea of just reducing the pacing rate as soon as you have seen a loss to 1.5x instead of 2.89, in a huge portion of circumstances seems to mitigate the worst behavior. There is a slight regression in certain edge cases. I'm still kind of trying to trace it down, like literally by looking at traces. And one source of the issue is definitely spurious retransmits. So if you accidentally declare loss and then realize, oh, that was a spurious retransmit, you don't go back up to the high gain in the current code. And that's partially due to the fact that BBR just doesn't know about spurious retransmits in the quick code. So I'm hoping that once I fix that, this will be completely neutral from an application metric perspective, saves over 5% retransmit rate globally, and it'll be a nice improvement. So the other idea, which is a little more recent, I haven't tested out as much, is the idea of reducing the congestion window gain when in startup. So normally, BBR uses a congestion window gain of 2 during probe BW. And the idea here is also use 2 in startup. The logic is based on the idea of rederiving kind of what congestion window you actually need in order to double every RTD. And in theory, it's only 2. Now, that's assuming a continuous delivery model, which is not reality in any way, shape, or form. And so there are some, there's a proposal to try to deal with that mitigation. But ideally, this would give you 40% less queuing delay when exiting startup, which would be particularly helpful for applications like WebRTC. Yeah. So, and Neil also recently rederived the pacing gain in BBR, and there's a link there to his derivation. And this is fairly similar, but quite a bit simpler. So, yeah, so to deal with the fact that we're assuming a continuous delivery model, we might need to deal with the aggregation of acts, which, at the very least, we're going to see 2 MSS acknowledged at once very often, and we may very well see quite a bit more. And so we don't want to slow our gain and slow our growth just because we're not providing enough congestion window early on in startup. But on the other hand, we don't want to provide a ton of extra congestion window and then just like completely run out. So I forgot to make one point verbally, which is my mistake. BBR is designed to be bandwidth based. And when it's bandwidth based, it's awesome. And this is where, if you look at traces, it works really well. It tends to fail pretty severely anytime it goes into a situation where it's congestion window based, because just weird things happen that are awful, for lack of a better description. And startup and exiting startup is one of the cases where, at least currently, you are always congestion window based, because by definition, you're sending it over 2 times the actual measured bandwidth. So one of 2 things is happening. Either your bandwidth is continually increasing, or eventually it tops out. And when it tops out, you build this queue. And there's no way to avoid building this queue, except for actually experiencing losses. So you basically either experiencing a lot of loss or build up a lot of queue. Those are the only 2 ways you can exit startup. And so that was one of the motivations of if we can reduce the CWIN gain, it actually might be even more effective than reducing, say, the pacing gain in terms of limiting the damage when exiting startup. So that was the thought process. Let's go back to ACK aggregation. Yeah, so as I said, the goal here really is to make sure that we have plenty of CWIN early on in startup, and we're not limiting by that. But as we get closer and closer to the plateau, we're getting closer and closer to having only a 2x CWIN gain, and we don't have to drain any extra packets. So the proposal is, I think Neil maybe in the Singapore IETF, and yes. And ICCRG there, he talked about this XS ACT approach, where you try to do ACK aggregation compensation by measuring periods where you see a delivery rate that's higher than the max bandwidth you've ever seen, kind of a short-term delivery rate, and saying, okay, well, sometimes I'm seeing basically stretch ACKs or aggregated ACKs. And you add that excess delivered to your congestion window. And the idea here is also add that to your congestion window, but instead of in the general case in Probe BW, we're actually putting a windowed filter on it, so you don't forget, what the excess was from a few RTTs ago. In this case, the proposal is just to add it to the instantaneous congestion window once when you see it, and that way it'll expire very quickly, because as BBR gets faster and faster, the excess ACT is going to naturally get smaller and smaller. So your actual bandwidth and your short-term bandwidth are going to get closer and closer is the hope. And so hopefully this kind of asymptotes to 2 or 3 packets, and then you have a nice stable exit, and you don't experience a lot of loss upon exit. The simulations look really good. You both exit startup faster, and you experience either less queuing delay or less loss, depending on kind of how you configure your buffer. But I don't have any experimental data yet, so it's a promising direction that hopefully is complementary to some of the things Neil's working on. The last proposal is to increase the drain pacing gain back to 0.75. Part of the motivation for this is that by kind of reducing the overhang, hopefully by reducing the CWIN gain to 2, we can afford to take about the same amount of time and drain, but drain a little less severely. As I said earlier in the talk, the Quartz folks or WebRTC folks were particularly hit by this 0.34 pacing gain that PBR is currently using during drain. And so they kind of need it increased for their application anyway. I imagine web traffic doesn't, love being drastically slowed down on their pacing rate either. So it may be a general purpose improvement. As Neil alluded, it actually also might allow us to unify two mechanisms that we have right now, which is drain and drain to target during probe BW. And so basically it might allow us to just enter the low gain phase of probe BW, get rid of the drain phase entirely, and kind of just meld those two things. So that would be nice. Yeah. So conclusion, in real world flows, flow startup is a huge problem for both Reno and Cubic and BBR. Real-time applications are even more sensitive to startup. And I think there are a lot of good ways to improve BBR as startup. And I'm kind of hopeful that maybe some of them are applicable to other congestion controllers, maybe PCC and other congestion controllers that people are working on. And if you want to experiment with any of these, I listed the connection options. That's kind of the standard quick way of running experiments. You throw them in what's the equivalent of transport params, but they're called connection options in the Google Quick version, and you can turn these on and off. And yeah, thanks for all the help and all the support from the greater BBR team, including Neil and Yichang and Dan and everyone. So, and questions for myself or Neil?
Thanks, Ian. If you have a couple of minutes, do you have any questions? Neil, do you want to come up? If there is a question for Neil.
Hi, it's Bob Brisgard. It's not really. Oh, sorry.
Praveen.
Hello.
Go for it, Praveen.
Yeah, hey, I have a few questions. A couple of questions to Neil. So in terms of, so the draft reflects V1, is there any plan to update the draft to reflect V2? The second question is, has V2 been deployed in production, and do you have any experimental results yet, apart from like the graphs you presented?
Right, so V2 has not been deployed in production, and I think once we have deployed V2 in production and have some real-world experience under our belt, then I think we will go ahead and update the draft to catch up with V2. We definitely do want to make sure that the draft reflects what's being used out there in the field, yeah.
I have another follow-up question. So in terms of being friendly to Reno and Cubic, there was a paper called COPA in NSDI, which has a mode to detect that there are other flows of, which are buffer filling. Have you explored any of that to maybe enter a more friendly mode when you detect that there are other flows like these?
Right, yeah, so that is an intriguing mechanism in that paper. We haven't done any experiments. Well, I guess early on in the BBR development process, we did do some lab experiments that were trying to do similar things, but we haven't tried out their mechanism. My gut says it's probably a very hard problem to make it work well in the real world. So, yeah, it sounds very challenging, but it does seem like an interesting area for research, yeah.
For the notes, can you repeat the name of the paper? I didn't get that.
I believe it was was it COPA? Was that the name of the?
It's COPA.
Yes,
yeah,
it's COPA. Yes.
Yeah, the most recent NSDI from paper from MIT.
Okay, I hadn't really got a question. It was just a point that Ian, you were saying, the WebRTC folk definitely want to avoid these spikes, and I just wanted to make the point that when you're looking at coexistences, not just with Cubic and Reno, it's with WebEx and Hangouts and all the other real-time things, not just WebRTC as well. There's all that has to work as well.
Definitely, yeah. A huge motivation for working with them is the idea that we can improve BBR for everyone by learning from real-time use cases that are a little more latency sensitive.
I'll add a quick note. The question that Praveen asked, I think, is relevant. The draft reflects V1, and I think there's a lot of detail in the slides for sure, but it'd be a lot of the rationale and a lot of bits are missing, obviously, because they can't go on the slides. We can talk offline, but we should think about some way of sharing this in a way that's more draft-like or some written-up form, so that people can, so that as thinking is evolving, people have some place to read and understand what's going on, perhaps even before coming to the meeting. But thank you for presenting it here. All right, we're going to move on to the next presentation. Brian, I suspect we won't have time for your thing. We'll unfortunately.
Hi, so I'm Ilpo Järvi, and I'm going to talk about retransmission timeout. So, and the seeming contradictory goal of making RTO fast due to random losses and slow enough due to congestion. So, next slide, please. So, currently the fast-slow RTO, which I call FASOR, is designed and specified for co-op, but you should not feel that this is just for co-op. It's just the environment where we found it very useful. So such environments are subject to random losses, and small exchanges are very common. And congestion typically occurs because of large number of the devices rather than large payloads. This is obvious that eventually when billions of IoT devices are going to be deployed, then we will hit some hotspots in density where there are very many devices parallel to each other. And one important thing is that there is just one message in flight per flow. So the RTO is the only mechanism. If you lose the packet, then RTO, you need to wait for the RTO to trigger. And like I said, FASOR is more general, so this could be applied to some other RTO mechanism in other protocols too. And the current co-op congestion control proposals have some issues. So traditionally, current algorithm has had this exponential backup, and besides that, it has kept this RTO, this packet of RTO until you acquire RTT sample, which is unambiguous. But these congestion control algorithms differ from that in the way that they do not return the packet of RTO, and we have shown the congestion collapse will occur when the RTT is large enough. So there are some conditions. I will not go through them to save time, and since they are specific to those algorithms. So, but anyway, when you have RTT long enough, the RTO triggers, and this is persistent condition under some conditions, also making the next exchange will also do the same thing, that the RTO is too small. But the thing which is also important for this presentation is that when these algorithms don't retain the RTO, they perform obviously better in the cases of random loss, where you would want to have the RTO to trigger as soon as possible. So this is where the FASOR comes in. So we try to find a good middle ground between these contradictory goals. So on the other hand, we want to improve random loss, but on the same time, we need to really handle congestion safely so that we don't cause this collapse. And in FASOR, there are two ways to calculate RTO. There's this fast RTO, which is similar to normal RTO, then this new slow RTO, and some back-off logic to select which RTO to use. So fast RTO is similar to what TCP uses for RTO computation. Expect we have done this small change that we initialize it to a smaller value in order to improve the RTO for short exchanges, but this is quite a minor point, I think. And then the new thing is this slow RTO, which is analogous to Karn's algorithm. So Karn algorithm is algorithm keeps the RTO until it gets the unambiguous sample. And we do this slightly different way. So when we get an unambiguous sample, we measure the time it took from the original transmit. So it's the worst case time that the packet could have been in transit. We don't know whether it was the RTT was from the original or some of the retransmissions, but we just take the worst case time and then apply some additional factor to this. So this is more conservative than Kahn's algorithm. I actually believe that this is actually what Kahn's algorithm is, should have done in this case. So it should measure the actual RTT, that the worst case RTT. So I think that Kahn's algorithm is not conservative enough necessarily. And then we have this novel back-off logic. So in Kahn's algorithm, you have two-state RTO logic, but we add additional states. So we have this fast, slow, fast state in between. So if I start from the first state, so this fast is the normal state where your network state is not dubious. You are getting acknowledgements without any retransmissions. And then if you get some or your RTO triggers, so you don't know for which segment you got the acknowledgement, you go to this next state, which is this fast, slow, fast. And we measure the slow RTO, and then instead of using a slow RTO directly like Kahn's algorithm approach would use, we have this fast RTO first to probe with this probe quickly, so that if there is random losses, we are able to retransmit quite soon, and this covers pretty high error rates quite well. And only as a second step, we apply the slow RTO if it's needed at all. If we get the response back quickly, we don't need to apply the slow RTO at all, because we already got a valid RTT measurement from this exchange. And if the slow RTO is not successful, we know that we have waited long enough to train unnecessary retransmissions that we possibly have made, then we continue with the fast RTO-based back-off series in that state. And since this fast slow state is such that it can still, in the case of unnecessary retransmissions, cause this ambiguity problem, so we cannot measure the RTT, we need this last state, so that we start with slow RTO, so that we get with high probability valid RTT sample, which is unambiguous. I will skip this because I spoke most. So then I will show some results from a test. This is quite typical, or not typical, but at least you would see something along these numbers in IoT deployments. So low bandwidth and RTT is quite high in this case. And we have this concept of flow, so there are number of parallel flows, and each of these flows perform in total 50 request response exchanges. And to simulate these small devices which exchange only small amount of data, we reset the congestion control state every now and then, so 1 to 10 messages randomized, and each of these flow does these exchanges until the 50 in total is done. And the response payload, which is for the bottleneck direction, is 60 bytes. And I will show two test scenarios. So we have this heavy congestion with buffer bloat. We have tested that actually up to 400 flows, but I'm only showing this largest with 400 flows. And we have varying buffer sizes, including infinite buffer, which basically loses no packets. So every packet you send to the network, it will be unnecessary retransmission with the duplicate copy. And without any unnecessary retransmissions, the RTT with this 400 clients and infinite buffer in this case is around 10 seconds. The link is, of course, error-free to keep the congestion level up. And then another case is for this random losses. So we have then parallel pores without congestion. The link is enough to satisfy those, and the error parameters are shown there. We have short error state and then slightly longer better state, and these alternate. So here are some results with this heavy congestion and buffer flow. So here we see the congestion collapse with the default COAP and COCOA. They make for this, to make these 50 exchanges, they do up to 250 unnecessary retransmissions. So 80% of the load is actually, or the traffic is of this unnecessary retransmission, and all these increase your RTT, so it's way above this 10 seconds. It's not shown on the slide, but if you want to look from the backup, you can see that it goes much larger than the 10 seconds. And with Fuzzer, we can have quite high reduction in the number of unnecessary retransmissions, because the new flows always start with this small RTO, so the initial RTO is small. We will keep making some unnecessary retransmissions, but this situation does not persist with Fuzzer like it does with these other congestion control approaches. And as a result, the flow completion time will be much better with Fuzzer. Then results with random loss. So here the fast RTO quick probe is able to cover most of the losses quite well, and enables Fuzzer to finish much faster. And we have to remember that these two variants which we compare against are unsafe to congestion. If they would handle congestion properly, they would get much worse performance than what we see in this test. And Fuzzer is able to lower the RTO successfully in contrast to what these other congestion controls or default COAP does not even have the concept of RTT measurement, so it's just keeping this initial RTO and starting to back off from there. Do you have some question related to this or general comment?
I think you just have one more slide finished.
Yeah, so I have just conclusion. So we believe that Fuzzer achieves good balance between handling random losses efficiently and also responding to congestion. It's slightly more aggressive than the traditional RTO algorithm based on Karn, but we try to make it in a safe way. Yes, so this is all.
Gori Fairhurst, thanks for doing this work, because I think the first time we did COAP, we kind of didn't really think about it, and we're now working on it, so it's good to see research in this space. So thanks. My question is simple. How much memory per endpoint do you need to keep to run your algorithm? Because they always ask this. Do you have an idea? Have you looked at this?
Well, of course, for the RTO estimation, and you need some memory, which is common to any algorithm which estimates RTO. And in addition, you need the state, but the logic itself is quite simple. So it's just this state which is on whether you receive the unambiguous RTT sample or ambiguous sample. You decide the next state, and then of course the back-off logic, but you need to anyway have this back-off logic so it doesn't increase complexity from.
Thanks. I guess we can talk about this in other places. Thank you.
Yep, this is, thank you for bringing the presentation here. This is an interesting, sort of very different type of congestion control question that we typically do not see in ICCRG, but there's work around this happening at the IETF, and this is the right venue for discussing approaches that people are presenting to congestion control in IoT-like environments. So thank you for bringing it. If there are any questions, talk to Ilpo, or yeah, I guess that's going to be the end of ICCRG. Thank you so much for tolerating the power outage and being good through the whole thing. See you in Bangkok. Oh, did you? Well, and. Yeah, 3:36. I don't want to keep people.
Yeah, of course, yeah, I know. And actually,
So that means your presentation of the.
Yeah, right, yeah. No, it's fine. So really, I mean, I'm basically over there because the IETF.
No, and I think it's a useful.
Is it a quick question or not? But I actually think I was doing so it wasn't your about that.
I'm so